Okay, number theory time. I'm going to start by going over the exam. Any questions before I do that? No? Okay. So number one is to solve some congruences. The first is 13x congruent to 1 mod 15. So we know that the greatest common divisor of 13 and 15 is 1. So there is a unique solution modulo 15. And you can find it in any one of a number of ways. I mean, you can always do trial and error, just try everything. Or if you want to be a little bit quicker, you know that 13 is the same as minus 2 mod 15. So 13x is the same as minus 2x mod 15. And 14 is like minus 1. So if you let x equal to 7, 13 times 7 is minus 2 times 7 is minus 14, which is the same as 1 mod 15. So x equals 7 is a solution. So the solution is all x congruent to 7 modulo 15. Right? I mean, there are many ways to solve the problem. That's one of them. Right? Any questions about that? One B, we want to solve 9x congruent to 6 modulo 15. And the greatest common divisor of 9 and 15 is 3. And 6 is congruent to 0 mod 3. So there are exactly 3 solutions modulo 15, right? Exactly the number of this GCD. How do we find them? Well, if 9x is congruent to 6 mod 15, if you divide everything by 3, 3x is congruent to 2 mod 5. What's the solution of this congruence? Well, this you can almost do in your head. 3 is not congruent to 2, 6 is not congruent to 2, 9 is not congruent to 2, 12 is congruent to 2. So x congruent to 4 mod 5, and we want the solutions mod 15. I mean, this is correct, but mod 15, the solutions are x congruent to 4, 9, or 14 mod 15. So either of these two forms of the solutions is completely correct. Any questions about this? Problem number 2 is the Chinese remainder theorem. We want to solve the system of congruences x congruent to 5 mod 13 and x congruent to 6 mod 15. And the fact that 13 and 15 are relatively prime means there is a unique solution modulo 13 times 15, which I think is 195. And how do we find it? Well, if x is congruent to 5 mod 13, that means x is a number of the form 5 plus 13y for some y, and that has to be congruent to 6 mod 15. which means 13y has to be congruent to 1 mod 15. We already solved this congruence. Y is congruent to 7 mod 15. So y is some number of any number that forms 7 plus 15z. And so x, which is 5 plus 13y, that's 5 plus 13 times 7 plus 15z. Let's see, 13 times 7 is 91 plus 5 is 96 plus 13 times 15, 195z. So the solution is all x congruent to 96 modulo 195. Okay. Any questions about that? Number 3 is again a problem with the Chinese remainder theorem. We want to solve x congruent to 1 mod 3, x congruent to 2 mod 5, x congruent to 3 mod 7, and the fact that 3, 5, and 7 are pairwise relatively prime implies there exists a unique solution modulo 3 times 5 times 7, which is 105. And you just solve these congruences. If you solve the first two, and then you solve that in the third. So x congruent to 1 mod 3, x congruent to 2 mod 5. Let's just work this out. So if x is congruent to 1 mod 3, that means x is 1 plus 3y. And if x is also congruent to 2 mod 5, this is congruent to 2 mod 5. So 3y is congruent to 1 mod 5. That means y is congruent to 2 mod 5. So y is a number of the form 2 plus 5z. And so x, which is 1 plus 3y, is 1 plus 3 times 2 plus 5z. 3 times 2 is 6 plus 1 is 7. This is 7 plus 15z. So any number that satisfies the first two congruences is congruent to 7 mod 15. And this number has to also to be congruent to 3 mod 7. So that means that 15z is congruent to 3 minus 7, which is minus 4, which is actually, just forget that's the 0. That's the same as 3 mod 7. And 15 is the same as 1 mod 7. So this says z is congruent to 3 mod 7, or z is 3 plus 7 times t for any integer t. So x, which is 7 plus 15z, is 7 plus 15 times 3 plus 7t. 3 times 15 is 45, plus 7 is 52. 7 times 15 is 105. So x is any number of this form. So x is congruent to 52 modulo 105. That's a solution to problem 3. Any questions about these? The first 3 problems are just numerical problems. You don't have to prove anything. It's just solving a congruence. And of course, if you have an answer, you should always check. So, because it's easy to make a mistake. So let's just check. (52 minus 1 is 51, which is 3 times 17. So 52 is congruent to 1 mod 3. 52 minus 2 is 50, which is 5 times 10. So 52 is congruent to 2 mod 5. 52 minus 3 is 49, which is 7 times 7. So 52 is congruent to 3 mod 7. So all 3 of our congruences work, and we check. And if we had made a mistake, checking will tell us 100% of the time whether or not we made a mistake. Any questions about that? Okay. Problem number 4. We're given a set of residues, a set of integers, and we want to show it's a complete system of residues modulo 7. So let's just make a table. Here we put a number, I don't know, A, and here let's put A mod 7. The least non-negative residue. So we're given the numbers 3, 13, 8, minus 9, 72, and 25. So 3 is congruent to 3 mod 7. 13 is congruent to 6. 8 is congruent to 1. Minus 9 is congruent to 5. 72 is congruent to 2. 25 is congruent to 4. So if you look at the least non-negative residues of these 6 numbers, you get the numbers 1, 2, 3, 4, 5, 6. So every congruence class mod 7 that's relatively prime to 7 is represented by one and only one of these numbers. So the set of these 6 integers is a reduced set of residues mod 7. I mean, you need to write that out, but I'm just saying it, so that's good enough. Okay. Any questions about that? Okay, problem number 5. We have the number 72, which if we factor it is 8 times 9 or 2 cubed times 3 squared. And we know by a theorem that phi of any integer m is m times the product over all the primes that divide m, 1 minus 1 over p. So phi of 72 is 72. The primes that divide 72 are 2 and 3. So you get 1 minus a half, 1 minus a third. This is 72 times a half times 2/3. This is 1/3 of 72. That's 24. Right. Problem number 6. We want to find the order of A mod 5 for A equal to 1, 2, 3, and 4. And we want to compute the order of A. That means the least positive integer such that a to that power is 1 mod 5. So of course, 1 to the 1 is congruent to 1 mod 5. So 1 has order 1. 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, which is 1 mod 5. That's the smallest power. That's the smallest exponent. So 2 is order 4. If you look at the powers of 3, you get 3, 9, 27, 81. The first power of 3, which is 1 mod 4, is 3 to the 4th, 81. Sorry, which is 1 mod 5. And 4 squared is 16, which is 1 mod 5. So 1, 2, 3, and 4 have orders 1, 4, 4, and 2, respectively. Questions? Number 7 is prove that if A is congruent to B mod M, then A to the K is congruent to B to the K mod M for all positive integers K. So one proof could be by induction on K. I mean, it's true for K equal 1, because A to the first power and B to the first power, A and B are congruent mod 1. So assume true for K, then A to the K plus 1, which is A times A to the K, but A is congruent to B, and A to the K is congruent to B to the K. So this is B to the K plus 1 mod M. So that's a proof by induction. And another proof just from high school algebra is that A congruent to B mod M, M divides A minus B. And if you look at A to the K minus B to the K, you learned how to factor that, or you're supposed to. A minus B times A to the K minus 1 plus A to the K minus 2B up to B to the K minus 1. This is an integer. A minus B is divisible by M. So this is divisible by M. So this is all divisible by M. That means A to the K is congruent to B to the K mod M. So this is a second alternative proof, if you like. Questions about this? Any of these? Problem number 8 is to use the definition of the Euler-Free function. What is the definition? Phi of M is the number of integers A such that A is between 0 and M minus 1, and the greatest common divisor of A and M is 1. So suppose you let M be P squared. The divisors of P squared are 1P and P squared. The greatest common divisor of M and P squared is greater than 1 if and only if P divides A, right? The only divisors of P squared bigger than 1 are multiples of P. So P has to divide A for the greatest common divisor of P squared to be bigger than 1. What are the integers up to P squared minus 1? Well, 0, 1, you get 1 times p. You'll get a 2 times p. Finally, you'll get a p minus 1 times p. 0 is 0 times p. These are the numbers from 0 to p squared minus 1. The numbers that are divisible by p, those are the multiples of p. 0 times p, 1 times p, 2 times p, up to p minus 1 times p. So the multiples of p are 0 times p, 1 times p, 2 times p, 3 times p, up to p minus 1 times p. And these are p numbers. These are all the numbers that have between 0 and p squared minus 1 that have a factor in common with p squared. All the others are relatively prime to p. So phi of p squared, you have p squared numbers and you throw away p of them, and that's phi of p squared. So that's using the definition of the Euler-Free function to prove the result. Okay, any questions about that? Number 9 is to prove that if P is prime, then the congruence class is mod P is a field. This was not an if and only if statement on the exam. It was just to prove this in one direction. So there's no reason to prove that if P is not prime, that Z mod PZ is not a field. This is all you have to prove. So we know Z mod MZ is a commutative ring for all positive integers M. So what you have to show is that it's a field. So must show if P is a prime, if A plus PZ is not 0, that is not PZ, then there exists a congruence class B plus PZ such that A plus PZ times B plus PZ is 1 plus PZ, which is equivalent to saying there exists an integer B such that AB is congruent to 1 mod P. But A plus PZ not equal to PZ means exactly that A and P are relatively prime, which means exactly AX congruent to 1 mod P, this congruence, has a solution, which we can call B. And if you can solve this congruence, every non-zero congruence class is invertible. So that's all you have to do. All right. Any questions about this? And problem 10 was to prove the theorem that I proved many times in class. AX congruent to B mod M has a solution if and only if B is congruent to 0 modulo the greatest common divisor of A and M. So let's prove it. Let's go from left to right. If AX is congruent to B mod M, if there exists such an M, then there exists an integer Y such that ax minus b is a multiple of y, or b is equal to ax minus my, and the greatest common divisor of a and m divides a, divides m. So the greatest common divisor of a and m has to divide b. So that's the proof in one direction. And then the proof of the other direction is the following. So suppose we let d be the greatest common divisor of a and m. So we know there exist integers x and y such that d is a linear integral combination of a and m. D is ax plus my. And if d, the greatest common divisor of a and m, divides b, that means b is d times some number q. So b, that's dq, but d is ax plus by times q. That's aqx plus bqy. Let's see. dx plus my. D is ax plus my, so dq is ax plus my times q. So that's aqx and mqy. Oh, perfect. So a times the number qx is congruent to b mod m. So this congruence has a solution. If the greatest common divisor of a and m divides b. Oh, that's all. That's the whole exam. Are there questions about any of this? No. Okay. So then we can move on. And according to our syllabus, we're about to start chapter 3. So this officially is lecture 18 on polynomials and primitive roots. So let's start with an example. Suppose we take modulus m equal to 7. And suppose I take the integer a equal to 2, and I want to look at the powers of 2 mod 7. So 2 to the 0 is 1. That's congruent to 1 mod 7. 2 to the first power is 2, which is 2 mod 7. 2 cubed is 8, which is 1 mod 7. Sorry. 2 to the first power is 2. Let me do this correctly. I'm jumping ahead. Two to the 0th power is 1. 2 to the 1st power is 2. 2 squared is 4. 2 cubed is 8, which is 1 mod 7. So if I keep taking powers of 2, 2 to the 4th, that's 2 times 2 cubed. That's 2 times 1, or 2. 2 to the 5th is 2 times 2 to the 4th, which is 2 times 2, which is 2 squared, which is 4. Everything is mod 7. 2 to the 6th is 2 times 2 to the 5th. That's 2 times 4, which is 8, which is 1 mod 7. 2 to the 7th is 2 times 2 to the 6th, which is 2 times 1, which is 2 mod 7. Of course, you could also say 2 to the 7th is 128. Divide 128 by 7, you also get 2, of course. So if you look, as you're taking the higher and higher powers of 2 mod 7, you get 1, 2, 4, and then it repeats 1, 2, 4. And then it would repeat again, 1, 2. If I did one more, 2 to the 8th, which is 2 times 2 to the 7th, which is 2 times 2, which is 4. And so on forever. So the powers of 2 mod 7 go 1, 2, 4, 1, 2, 4, 1, 2, 4, and so on forever. Even if you took negative powers, let me take negative powers. What's the inverse of 2 mod 7? The inverse of 2 is 4, because 2 times 4 is 8. 2 to the minus 2, this is the inverse of 4. The inverse of 4 is 2 mod 7. What is 2 to the minus 3? You know, again, remember, 2 to the minus 3, this is like 2 cubed inverse. 2 cubed is 8, 8 inverse. 8 is 1, inverse of 1 is 1 mod 7. Right? You just get the same numbers, 1, 2, and 4. That's all you ever get taking powers of 2. So 2 to the k, congruent to the other non-zero residues modulo 7. What are they? 3, 5, and 6. Never mod 7. So a power of 2 is never congruent to 3, 5, or 6 mod 7. Okay, that's interesting. That's because 2 is order 3, so you're only going to get 3 different numbers mod 7. Those 3 different numbers are 1, 2, and 4. That's all you ever get. Right? So 7's a nice number. Let's keep looking at it. Suppose I want to look at the powers of 3 mod 7. So 3 to the 0th power, of course, is just 1 mod 7. 3 to the 1st power is 3. 3 squared is 9. What is 9 mod 7? It's 2. 3 cubed is 27. Mod 7, that's 6. 3 to the 4th is 81. If you divide 81 by 7, you get 4 mod 7. 3 to the 5th is 243. If you divide 243 by 7, you get 7 goes into 33, 20, you get 5 mod 7. Of course, we know by Euler-Fermat's theorem, phi of 7 is 6. So 3 to the 6th has to be congruent to 1 mod 7. So when you get to 6, 3 to the 6th is congruent to 1 mod 7. I mean, it's 729, but it's congruent to 1 mod 7. And now, this is what you see when you take the powers of 3. What congruence classes do you get? You get every non-zero congruence class. 1, 2, 3, 4, 5, 6. So the set of powers 3 to the I, mod 7, where I is 1, 0, 1, 2, 3, 4, and 5, is a reduced set of residues modulo 7. Every non-zero congruence class is congruent to a power of 3 mod 7. So with the powers of 2, you only got 1, 2, and 4. But with the powers of 3, you get everything, every non-zero congruence class. And that is a very interesting phenomenon. And we give this a name, this kind of thing a name. So if you take for any positive integer m, there are phi of m congruence classes in Z mod mz relatively prime to m. And we say that the integer a is a primitive root modulo m. We can state this in 2 equivalent ways. More than 2 equivalent ways. If the set of integers 1a, a squared, a cubed, all the way up to a to the phi of m minus 1 are pairwise incongruent modulo m. So here we have phi of m integers, and there only are phi of m congruence classes relatively prime to m. So another way of saying that is if, so this is one possibility. Another way of saying is that this is a reduced set of residues modulo m. And another way of saying this is the following. A is a primitive root modulo m if a and m are relatively prime, and for every integer b such that b and m is relatively prime, there exists a positive power k such that a to the k is congruent to b mod m for every b. So for example, 3 we just saw is a primitive root modulo 7. 2 is not a primitive root modulo 7. So this notion of a primitive root makes sense for a modulus, whether it's prime or not, but it doesn't mean that primitive roots exist. See this? Look at some examples. Suppose I take m equals to 10. So what is phi of 10? Well, 10 is 2 times 5. So this is 10 times 1 minus a half times 1 minus a fifth. That's 10 times a half times 4 fifths, which is 2 fifths times 10, which is 4. And what are the congruence classes relatively prime to 10? So a reduced set of residues modulo 10. So what are the numbers from 1 to 10 that are relatively prime to 10? 1, 3, 7, and 9. Let's look at the powers of 3. 3 to the 0 is congruent to 1 mod 10. 3 to the first power is congruent to 3 mod 10. 3 squared is congruent to 9 mod 10. 3 cubed is 27, is congruent to 7 mod 10. So the powers of 3 give you 1, 3, 9, and 7, give you all of them. So 3 is a primitive root mod 10. You know, by what happens if you take higher powers of 3? Well, 3 to the 4th, that's be the next power. But 4 is phi of 10, that's 3 to the phi of 10. And we know by Fermat, we don't even have to do the calculation, this is congruent to 1 mod 10. Of course, 3 to the 4th is 81, which is obviously congruent to 1 mod 10. So either from Fermat or from arithmetic, we see that. Okay. Any questions about this? Let's look at one more example. Suppose I take the modulus m equal to 8, which is 2 cubed. So phi of 8 is 8 times 1 minus a half, which is 4. And a reduced set of residues modulo 8. Well, what numbers are relatively prime to 8? The odd numbers, 1, 3, 5, and 7. Is there a primitive root? Well, any power of 1 is 1 mod 8. That's never a primitive root. 3 squared is 9, is 1 mod 8. So the powers of 3 are just 1 and 3. 5 squared is 25. That's also 1 mod 8. 7 squared is 49. That's also 1 mod 8. So modulo 8, the square of any number that's prime to 8 is 1. So there's no primitive root. Like the powers of 3 just give you 1 and 3. The powers of 5 just give you 1 and 5. Powers of 7 just give you 1 and 7. Powers of 1 just give you 1. So there exists no primitive root mod 8. So primitive roots don't always exist. But for us, in the most important case, they do exist. So there's a theorem. We'll prove it not today. The theorem says that there exists a primitive root modulo p for every prime p. So we saw, for example, that 3 is a primitive root mod 7. But some numbers other than primes have primitive roots. We saw that 10 has a primitive root. So,
Professor,
yes,
quick question. There could be more than one primitive root?
yes,
Okay.
yes, the primitive root is not unique. And we'll actually prove a theorem that says how many primitive roots there are. So, for example, every prime p has exactly phi of p minus 1 distinct primitive roots mod p. So, for example, if p is equal to 7, p minus 1 is 6, phi of 6 is 2. So 7 should have 2 primitive roots. And let's say, suppose I take a equal to 5. So 5 to the first power is 5 mod 7. A squared, or 5 squared, is 25. 25 is 4 mod 7. A cubed, or 5 cubed, that's 5 times 5 squared. That's 5 times 4, which is 20, which is 6 mod 7. 5 to the fourth is 5 times 5 cubed, is 30, which is 2 mod 7. 5 to the fifth is 5 times 2, which is 10, which is 3 mod 7. So if I take the powers of 5, I get, oh, and of course, 5 to the sixth is congruent to 1 mod 7. So if I take the powers of 5, I get 1, 2, 3, 1, 2, 3, 4, 5, 6. So modulo 7, 5 is also a primitive root. We saw that 3 is a primitive root and 5 is a primitive root. And those are the only 2 primitive roots there are. So the primitive root is not unique generally. Now, the way we're going to prove our theorem about primitive roots uses polynomials. And you learn about polynomials in, I don't know, high school or high school algebra, and you spend a lot of time in calculus differentiating polynomials. And so a polynomial, they don't have to have real or integer coefficients. They can be coefficients in any ring R, commutative ring. Like the integers are a commutative ring. It's just an expression of the form am x to the m, am minus 1, x to the m minus 1, plus a1x plus a0, with these coefficients, a0, a1 up to a sub m, in the ring R. And the degree of f of x, if f of x is not the zero polynomial is just 0, all the coefficients are 0. The degree of f of x is the largest coefficient, a sub n, that's different from 0. And you have to say that because, I mean, if you write a polynomial like, sorry, this should be f of x, like f of x equals 7x cubed plus 2x squared minus 9. So the largest, or it's the largest, I should say, the degree of f of x is the largest integer n, where the coefficient an is different from 0. So in this polynomial, this is like a3 x cubed plus a2 x squared plus a1x plus a0. A3 is 7. A2 is 2. A1 is 0. A0 is minus 9. So the largest non-zero coefficient is A3. So this has degree 3. But it's not illegal to write this f of x also in the form of 0 times x to the 4th plus 7x cubed plus 2x squared plus 0 times x plus minus 9 times 1. So here, the coefficient A4 is 0. So even though I have an A4 coefficient, the degree isn't 4 because the coefficient of x to the 4th is 0. It's still the coefficient of x cubed that has the largest, that has a non-zero coefficient, and the power of x is the largest. So this is just being sort of careful about the definition of a degree. So there's nothing wrong with writing a polynomial like this, but this polynomial, even though you see this term x to the 4th, the coefficient is 0, and this polynomial does not have degree 4, it still has degree 3. And so the 0 polynomial, however you write it, f of x equals am x to the m. All of the coefficients are 0 for all I. And the 0 polynomial has, we don't assign a degree to the 0 polynomial. But a non-zero constant polynomial like f of x equal a0 different from 0, this has degree 0 because the largest n such that an is non-zero, in this case is 0. So a non-constant polynomial has degree 0. A non-zero constant polynomial is degree 0. The 0 polynomial has no degree. And the leading coefficient, so if we have f of x equals an x to the n and so forth, with an different from 0, so this has degree n, this n is called the leading coefficient. Of the polynomial. So I know my writing's illegible, but the book is legible. And a polynomial is monic if the leading coefficient is 1. And again, you know from, I don't know where, high school or preschool or pre-calculus or somewhere, how to add and subtract polynomials, right? If you have f of x equals 3x squared plus 9x plus 17, and g of x is x cubed minus 2, then f of x plus g of x is x cubed plus 3x squared plus 9x plus 15. And f of x times g of x, you multiply term by term, you get 3x to the 5th and a lot of terms and minus 34, right? So it's obvious by the time you get to math class at 300 level, you can add, subtract, and multiply polynomials, and you should even be able to divide polynomials. So, and there is a theorem which formalizes what you know about division of polynomials. It's called the division algorithm. For polynomials. Right, so you remember the division algorithm for integers. So if you had given integers I'll call them f and d, with d different from 0, there exist unique integers q and r such that f is d times q with a remainder r, and r is between 0 and d minus 1. So that's the division algorithm for whole numbers, for integers. And the division algorithm for polynomials says essentially the same thing. It says that f be a field like the rational numbers or the real numbers or the integers mod p for a prime, that f be a field and take two polynomials, f of x and d of x. And when I write f squared brackets x, this just means the ring or the set of all polynomials with coefficients in x. So it just means take two polynomials. There exist unique polynomials q of x and r of x. These are just like the quotient and the remainder when you're dividing integers, such that f of x, the polynomial, when you divide by d of x, you get d of x times this quotient q of x plus the remainder r of x. And what makes everything unique is the condition on the remainder. Either r of x is 0 or the degree of r of x, means r of x is not 0, so it has a degree, is strictly less than the degree of d of x. I mean, that's the division algorithm for polynomials. So it's just long division, which you're supposed to know. So let's just do an example. Suppose I take d of x equal to x squared plus 1 and f of x equal to, I don't know, 3x cubed minus 2x plus 7. And my field is going to be the rational numbers. So if I divide f of x, so the division algorithm says there exist polynomials q of x and r of x such that f of x is d of x q of x plus r of x, and either r of x equals 0 or the degree of r of x is less than the degree of d. The degree of d is 2, so the degree of r of x is either 0 or 1. And how would you find such a thing? Well, you do just what you do in high school. You divide x squared plus 1 into 3x cubed minus 2x plus 7. I guess this is how you do it. So x squared into this goes 3x times. I get 3x cubed plus 3x. When I subtract, I get minus 5x plus 7. Oh, this doesn't go into this at all. So this is my remainder, and this is my quotient. That is, take x squared plus 1 times 3x plus minus 5x plus 7. If I did everything right, this is equal to 3x squared minus 2x plus 7. So this is my d of x. This is my quotient. This is my remainder. And this is what I started with, f of x. Any questions about this? Question? Okay. Here, just for fun, I'll give you a problem to do with long division. Suppose f of x is 2x to the fourth plus 3x cubed plus x squared minus 1. And you're going to divide it by x squared plus 1. Find the quotient and the remainder. So spend a minute doing that. Right. So you're dividing x squared plus 1 into 2x to the fourth plus 3x cubed plus x squared minus 1. Did anyone get the quotient and the remainder? Let's see. X squared into 2x fourth goes 2x squared times. So you get 2x to the fourth plus 2x squared. When you subtract, you get 3x cubed minus x squared minus 1. X squared plus 1 goes into this 3x times. So you get 3x cubed plus 3x. When you subtract, you get minus x squared minus 3x minus 1. X squared plus 1 goes into this minus 1 times. I get minus x squared minus 1. I subtract, I get minus 3x. And x squared plus 1 doesn't go into that. So this is my quotient, and this is my remainder. So 2x to the fourth plus 3x cubed plus x squared minus 1 is x squared plus 1 times 2x squared plus 3x minus 1 plus this remainder of minus 3x. So if I did my algebra correctly, maybe not.
Professor, you forgot the x for -3.
Sorry?
You forgot, yeah.
Yeah, thank you. Yeah. So if I did my algebra correctly, this is the division algorithm in this instance. Okay, so how do you actually prove the division algorithm? So this is really something you need to work through step by step at home, because there's a little bit of notation involved that takes a while to get used to. So we have a polynomial f of x, and we have a polynomial d of x. Let's say we write d of x is b sub m x to the m, bm minus 1 x to the m minus 1 plus b1x plus b0. So this is a non-zero polynomial. You can only divide by a non-zero polynomial. And suppose bm is different from 0, so the degree of d of x, and I'll just write degree of d, is equal to m. So there are two cases. The first is very simple. Case one is d of x divides f of x. That just means that f of x is d of x times q of x for some q, and let r of x be 0. And we have f of x is dq plus r, where r is 0. So in that case, in terms of at least the existence, not the uniqueness of the quotient and the remainder, we're done. So in the second case, d of x does not divide f of x. And what that means is for every polynomial q, or q of x, I'm just going to write f for f of x and d for d of x. For every polynomial q, f is not equal to dq, or f minus dq isn't 0. So this is a non-zero polynomial. So the degree of f minus dq is a non-negative integer. Greater than or equal to 0. And by the minimum principle, every non-empty set of non-negative integers contains the smallest element. So choose a polynomial q such that the degree of f minus dq is the smallest non-negative integer that can be represented in this form. The minimum principle says that every non-empty set of non-negative integers has the smallest element. So suppose the degree of f minus dq is L, some non-negative integer. So if we let f of x minus d of x q of x, that's some polynomial I'll call r of x, and it has degree L. It's c sub L x to the L down to c1 x plus c0, where this leading coefficient CL is non-zero. And I claim that L is less than M, which is the degree of D. All right, if I can show that, then I proved half my theorem. I proved you can always write F as dq plus R, where R is either 0 or has smaller degree than D. So this is a proof by contradiction. So I'm going to suppose that L is greater than or equal to M and get a contradiction. So remember, d of x is b sub m x to the m plus lower order terms. And bm is not 0. But we're in a field, so it has an inverse. So if we look at b sub m inverse d of x, I'm just multiplying every, see here, the next term is bm minus 1 x to the m minus 1. If I'm multiplying by bm inverse, this coefficient becomes 1. plus b sub m inverse b sub m minus 1 x to the m minus 1 down to b sub m inverse b0. This is a monic polynomial. It is degree x to the m. And if I multiply this by the power x to the L minus m, because I'm assuming L is greater than or equal to m, so this is a non-negative power of x, times c sub L, right? C sub L is the leading coefficient of this remainder. I'm multiplying this by c sub L, and I'm multiplying by x to the L minus m. This is x to the L plus lower order terms. I mean, the last term I get is b sub m minus 1 b0 c sub L x to the L minus m. In any case, this polynomial is a polynomial of degree L. And so let's just sort of summarize what some of this algebra is. So it's getting slightly messy. So I started with a polynomial f of x and a non-zero polynomial d of x. And I found a quotient q of x and a polynomial r of x, such that f of x is d of x, q of x plus r of x. And the degree of r of x is non-zero and as small as possible. Degree of r of x, we call it L. And I want to show that L is less than m, which is the degree of d of x. If not, I constructed this polynomial, which has leading coefficient c sub L and degree x to the L. Suppose I let capital Q of x be this polynomial. This is my Q of x, little q of x. Actually, I'm just going to add this b sub m, c sub L, x to the L minus m, b sub m inverse, right? B sub m inverse, c sub L, x to the L minus, this is just a monomial. So that Q of x equal to this. This is some polynomial with coefficients in f. And let capital R of x be the polynomial f of x minus d of x times capital Q of x. What is that? This is f of x minus d of x times little q of x plus b sub m minus 1 c sub L x to the L minus m. This is f of x minus d of x q of x minus bm minus 1 c sub L x to the L minus m d of x. F of x minus d of x q of x, that's r of x, little r of x. minus this expression. R of x, you remember, had degree L. It was C sub L x to the L plus some lower order terms. And then I'm subtracting this. And that Bm minus 1 d of x, that was a polynomial whose leading term was CLX to the L. Plus other stuff. And you'll notice these two terms cancel. So what we're left with is a polynomial of degree at most L minus 1. So f of x minus d of x q of x, this is a polynomial which is either 0 or has degree less than L minus 1. It can't be 0. And it can't have degree less than L minus 1 because L is the smallest degree of any polynomial of this form. So this is a contradiction, which means L has to be less than M. So this is a proof of half of our theorem. What we just proved is that given f of x and d of x, where d of x is non-zero, there exist q of x and r of x, with f of x equals d of x, q of x plus r of x. And either r of x equals 0 or the degree of r is less than the degree of d. And now I want to prove uniqueness of the quotient and remainder. So suppose we have two representations of this form. Suppose f of x is d of x q1 of x plus r1 of x, plus, and it's also d of x q2 of x plus r2 of x. And the degree is in either r1 equals 0 or degree of r1 is less than m, which is the degree of d, and that's true for I equal 1 and 2. So of course, if r1 of x is 0, then d of x divides r2 of x. R2, if it's not 0, it has degrees smaller than d and can't be divisible by d. So R2 is 0. So R1 is 0 if and only if R2 is 0. If R1 of x is not 0, then if I rearrange this equation, d of x times q1 of x minus q2 of x is R2 of x minus R1 of x. So d of x divides this polynomial. These are each polynomials of degree less than m. So this has degree less than m, or is 0. D of x is degree m. A polynomial of degree m cannot divide a polynomial of degree less than m. So this has to be 0. So r1 of x equals r2 of x, and q1 of x equals q2 of x. Okay, so this was a lot of work. I mean, it's a lot of work. It's a very nice theorem. It's completely proven in the book, and it's legible, and it's worth spending a lot of time trying to understand it all. Any questions about this? This is really getting to be interesting mathematics. All this is proving is what you learned in high school, namely that you can divide one polynomial by another. And this is a formal proof that what they taught you to do algorithmically in high school is always correct. All right. If there are no questions, then we will quit for the day. Everyone stay well. It's a nice day, it looks like. Be back on Wednesday. Bye all.
Professor, I got a question though. When are the office hours for today?
Today, they're not office hours, but there'll be office hours Tuesday, Wednesday, and Thursday.
Oh,
I haven't posted them yet. I try to have like a morning, an afternoon, and an evening. Do you have a preference?
anything will do, anything.
Okay, all right. So, yeah, I didn't schedule one for today, and I always like to schedule them at least a day in advance. So I will have office hours for the rest of the week. And there'll be an email that I send out this afternoon with the times. Okay, anything else? All right.
That's it.
All right, bye all.